All right, so today we move into chapter 13, radiation exchange between surfaces. This is how a mechanical engineer would make the calculations to quantify radiative heat transfer. The previous chapter was purely theoretical and mathematical, and it was foundational. But here we make some approximations. So we're very much interested in calculating what they call a view factor, how well surfaces see surfaces. And then we can, hopefully by the end of today, make some black body radiation exchange calculations. So all of our surfaces in an enclosure will be black, and how much heat is transferred from a hot surface to a colder surface via radiation. If we look ahead, I don't think I'm going to have much time to cover this. It's important, but I mentioned in chapter 12 that radiation exchange with participating medium like a gas is challenging mathematically. So we're going to pretty much stay with surface to surface radiative heat transfer. So the key idea is view factor. Well, what is the view factor? The view factor, given by the symbol F, I, comma, J, is the fraction of the thermal radiation that leaves a surface I and is intercepted by surface J. When you're introduced to a definition, you really pay attention to the words because they're loaded. They mean something. So it's a fraction. So the view factor goes between what value and what value? 0 and 1. 0 and 1. The radiation that leaves surface I. How can it leave a surface I? How can photons go away from surface I? Both by emission as well as being reflected off of the surface. Now what we're going to do is we're only going to consider diffuse surfaces. So it's diffuse in its emission and diffuse in its reflection. So it's all diffuse surfaces. Now the other word that's worth looking at is intercepted by surface J. So there's another surface J. The photons go there. What happens? They only strike or hit or are intercepted by surface J. Does it say anything about they're absorbed? Didn't say that. It's just they're intercepted, that they strike surface J. Well, how are we going to go ahead and calculate this view factor? Well, put in a surface I. Here's one. And often the side of interest of the surface is what's important, but I try to hash the other side where there's conduction to keep the surface that hot or keep it that cold at a given temperature. But this is here surface A sub I. We then pick another surface over here, and that's surface A sub J. Okay, so what do we want to do is we want to get the fraction of the radiation that leaves surface I. So what do is you say, I'm going to sum up over little segments of I. So consider little d sub AI. And when you have defined that little d sub AI, you characterize it orientation by an outward normal directed unit vector. So that's the normal vector coming off of that I. That normal vector over here would be a different vector, wouldn't it? All right. Now a photon may leave and it may strike surface J. Maybe it leaves and goes in that path right there. Boom. So it hit a small segment, d sub AJ, of surface J. Okay, well, d sub AJ has an outward directed vector 2 that's perpendicular. See, this is perpendicular, that's perpendicular. And by defining those two perpendicular directions, or normal directions to the surfaces, what do we have right here? Theta I, the polar angle. And what about this angle right here? Theta J. Theta J. So we have both the angle theta I and theta J. Well, that impacts the amount of photons, or the fraction of radiant energy leaving I that impinges on J. All right. The other parameter of interest is R. R is the distance from that location on I to that other location on J. So here's the big equation. We're going to drive it in a second. But here's the equation for the fraction of photons that are diffusely coming off of surface I due to either emission or reflection, which go and impinge or strike or hit surface J. It's equal to an integral of cosine theta I cosine theta j divided by pi r squared. And so the integrand of that integral, we can tell, we know what each of these terms mean. The cosine of that angle, theta I, cosine of the other angle, theta j, the distance squared, and pi. What do we integrate over? Well, we integrate over d sub aj. Integrate over the entire second surface j. But that's the inside integral. You also have an outer integral, d sub ai, integrate over the entire surface a sub I. And the view factor, I didn't leave enough room. Let me scoot this over a little bit. Okay, it won't let me scoot it over. I'll just erase it then. I left out, it's 1 over ai times that double area integral. That's the view factor I to j. So this is the most important equation, or one of the most important equations in this here chapter. It's how do I calculate that fraction? So before we derive it, let's just pause, take a good look at it. I tried to emphasize what is theta I, what is theta j, what is r, okay? And it's a double area integral. How would you do that double area integral? Have you seen an integral like this before in any engineering class or physics class or math class? Where'd you see it? Cal 2? Are you sure it's not just an area integral, but a double area integral? Do me a favor, take a look in your book. Try to find where there's a, not just an area integral or a volume integral, but a double area integral, especially in physics or engineering. If I wanted to do this numerically, what would it look like? Well, we already started the discretization of surface I. So you bust it up into a lot of little DAI segments. You'd also bust up, just like we did over here, DAJ into a bunch of segments, little DAJs. Okay. Then I would go to the first segment of area I, and I would draw a line to the middle of each segment of area J. So it'd go like this, then like this, then like that, then like that, then like that, all the way to the very last one. Then for each of those line segments, I'd calculate not only the R, I'd calculate the theta I and theta j so I could get the cosine of both of them, divide it by pi r squared. That is kind of going from one DAI to all of the DAJs, summing them up over j's. Then move to the next one and do the same thing. Then move to the next one, then move to the next one, and finally you'll get down to the very last one, and then you'll try and do the same thing. Like that. That's how you would compute it numerically. It wouldn't be too good in converging, and you'd have to do some checking to make sure that the line segment actually can make it there without any obstructions, right? So if this surface went all the way around here, right, that's the whole area I, is this little segment over here going to be able to go and see J? But part of it does, but not the other part doesn't. So it can be numerically a little challenging. But this is the big equation to calculate. So let's ask some questions. I already asked question 1 and question 4 from the previous class. So you get a choice from question 2, 3, or 5. Which question would you like to handle first? 5. Let's go right for 5. Somebody shouted out 5. So there's question 5, and so we start. So the question for question 5 is the integrand in the view factor equation, cosine theta I times cosine theta j divided by pi r squared. Can the integrand ever be negative? Yes or no? Can the integrand, can this part be negative? Can this part right here be negative? All right, well, let's do this. It can be negative if the cosine of theta I is negative and everything else is positive, or that the cosine of theta j is negative and everything else is positive, or that pi is never going to be negative. How about r? Well, you're squaring it. R is a distance. That's always positive. So this is always positive, always positive. So now the question is cosine of theta I. But think about a little itty bitty segment. You come out with the normal n, and then you're going to be sending out photons in a cosine distribution, right? Are you ever from that surface going to send out photons in that direction, which would give you a theta greater than pi over 2, and a cosine of a theta of pi over 2 is negative, isn't it? But can you ever send photons back into yourself? That doesn't make sense. I mean, it's emitting going out from the surface. True? So isn't this always going to be positive? And isn't this always going to be positive? And so it's always going to be positive. It can never be negative. So can the integrand be negative? No. Okay. Do you want 2 or 3? Which one do you want to? Yes, sir. Yeah, that's I and j. Thank you. How about 2 or 3? 2. He wants to go for 2. Can the view factor fi to j equal 0? Yes or no? All right, so can the view factor equal 0? Sure. And when would that be? When they're blocked. They can't see each other. There's no photons that'll leave I and hit on J or impinge on J. You know, just so one good example would be here is surface. Whoops. Here is surface I pointed that direction. Here is surface J pointed that direction. Not going to happen. So, yes, it can. Hey, what were you thinking? All right, well, move on. Let's do the derivation of that complicated equation. And I look forward to anybody, if you could show me out of another textbook, another class that you've taken at the university, a double area integral, which is meaningful. But this is a main part of thermal radiation, the view factor. There's no heat transfer textbook that doesn't show you the view factor and doesn't show you the equation that I've shown you for the double area integral. So how do they derive this equation? Well, you just start from, you take into account all that leave I and that hit J. And you divide it by all of it, the photons, the emission, that leave I. Okay, well, what leaves I? It's either due to emission or reflection. We're going to assume that it's diffuse reflection, diffuse emission, and it's coming off the surface I. Well, we would then multiply by the cosine of the angle theta I, multiply by the solid angle that it goes to for the whole hemisphere. That will integrate over the whole hemisphere for the solid angle, and that will be everything that leaves I. We're going to work on the denominator first. And then we integrate over the area. See how we have this integral? Does that make sense? That's what all of the watts that leave I. Okay. So if we have uniform intensity because it's diffuse surface, that comes outside the integral. And now we just have to substitute for what is d omega. D omega is that sine theta I, d theta I, d phi, and then you integrate over the solid angle, theta 0 to pi over 2, phi from 0 to 2 pi. Haven't we done that integral before? Over the hemisphere? We did, didn't we? And so that integral turns into 1/2 of 2 pi minus 0, which is simply pi. And so what we find is that I continues down in the equation, and you get then integrate over the area so that the total leaving surface I is the product of pi, the intensity of the outgoing radiation flux due to emission of radiation, and the magnitude of the surface area. Well, J is simply that radiosity. So the radiosity times the area is what leaves. Pretty simple result for the denominator. Now let's work on the numerator. So if you work on the numerator, you have the same type of equation. What's leaving? That's going to be a constant. We'll pull it outside. It's cosine distributed because it's diffuse. The solid angle now is not going to integrate over the hemisphere. We're just going to integrate over the solid angle that goes and hits surface J. Well, that's a different way of representing d omega, the solid angle. Here it's the cosine theta j daj, so it's that normal area at the end of a little cone of solid angle d omega. So it's cosine theta j divided by daj divided by r squared. That's what d omega is. Put the equal sign there. So you substitute that in there. And then again, we're just going to repeat, we're going to use the radiosity and note that this I is constant. And so we have J times the cosine theta I, cosine theta J divided by pi r squared. So the pi comes from this term. The r squared comes from the d omega, and the two cosines come from this cosine distributed nature of the radiation. And so the numerator is put over top of the denominator, the j's cancel, and you get the equation. There's that equation. All right? All right. Well, there's two rules which come into play. One is called the summation rule. Think about a surface, let's say 1, and it's in an enclosure made up of another surface 2, another surface 3, and another surface 4. 4 surfaces make up the enclosure. Okay. And now you say to yourself, the fraction of the photons that leave 1 and hit 2, plus the fraction of the photons that leave 1 and hit 3, plus the fraction of the photons that leave 1 and hit 4. What does that sum up to? The fraction that leave 1 and hit either 2, 3, or 4. Sums up to 100%. Yeah. And so that's a summation rule. It's like the sum of all of them that leave have to go somewhere. Okay. There's a little challenge. Let's say I leave surface 2, 3, and 4 like that. So this is 2, 3, and 4. But we change surface 1 and we make it look like this. What's different now in that system? Surface 1 is, well, how would you describe surface 1? Concave, right? What would be different in the summation rule? Or thinking about photons that are leaving surface 1. It could leave 1 and hit 1. And that's always, hold it, what are you talking about? The photons that would leave surface 1 when it's planar, are any of them going to hit 1? No. But if you have a surface 1 like we've shown here, what did we call that? Concave? Some of them could leave surface 1 and go and impinge on surface 1. So how does that change the summation rule? We would have the fraction that leave 1 hit 1 plus the fraction leave 1 hit 2 plus the fraction leave 1 hit 3 plus the fraction leave 1 hit 4 is equal to 1. So often this term is 0. How do we generalize it? We would say the sum of the view factors from any surface I to all of the j's in an enclosure, including I. J has to include the summation I, must equal to 1. And that's the summation rule. 100% taken into account. All right. There's another rule called the reciprocity rule. And you know I like to look at dictionaries, online dictionary, when I'm confronted with a word that you don't use every day, right? But some of you know already what reciprocity means. Reciprocity. So this is what I do. I just go and type in, define a term, and then I read the definition of the term reciprocity here. The key idea in reciprocity is there's a reciprocal nature to it, in some sort of mutual dependence or action or influence. Well, here it's action. So in radiation heat transfer, if I have a surface I and it's sending out photons, and then I have a surface J, and some of those photons from I impinge on J, guess what the photons from J can do? Some of the photons emitted from J can go back and impinge on I. And that's the whole idea between reciprocity. If I can see you, you can see me. If the photons from my surface are going to strike you, the photons from your surface are going to strike me. So mathematically, what does that look like? Well, write out the view factor twice. The view factor from I to J is equal to 1 over a sub I, double area integral dAj dAi, the cosine theta I, cosine theta j divided by pi r squared. Did I write that equation correctly? Yeah, that looks okay. Let's write out the view factor from J back to I. How would it change? Is it 1 over a sub j? Double integral area dAi dAj cosine theta j cosine theta I divided by pi r squared. Did I write it correctly for J back to I? So you take a look. There's no difference in the pi and r squared, right? That part of the integrand, I'm sure. If I just switch the order here, does it change the result? No. So the integrand is exactly the same in those double area integrals. How about this? I think this is your question, right? You said, does it matter if you integrate with respect to J first and then I, or could it be I first and then J? What about the order of the integration? It can go either way. Mathematically, it's not going to have a different effect. So the only difference is in this equation between Fij and Fji is that I divide that double area integral by either a sub I or a sub j. True? So what I do is I'll just multiply this equation by a sub I, multiply this equation by a sub j. What about the right-hand side of both sides of these equations? Aren't they the same? There is now the reciprocity rule. The area I times the view factor from I to j is equal to the area j view factor j to I. In certain cases, Fij equals Fji, but that's not very common. It's more rare that the view factors are equal. But it's always true that the area F is equal to the area F product. Let's employ some of these principles of summation and reciprocity to solve for simple view factors in certain cases. So consider two concentric spheres. The center of both spheres are at the same location. One sphere is a diameter d1, and another sphere is diameter d2. And so we're interested in radiation exchange, or how surface 1, which is the outside of D1, and surface 2, the inside of the second sphere, see each other and how they might radiatively exchange energy back and forth. So there's a pile of view factors. We could talk about the view factor 1 to 1, the view factor 1 to 2, the view factor 2 to 1, the view factor 2 to 2. There's 4 view factors that we can look at and calculate. All right. So probably one of you says, I think I can tell you with confidence what one of those 4 view factors are. How about I pause and walk around? All right, so you got it? You got all 4? You got all. Frank has all 4. Anybody else have all 4? You do? Really? 2 people? All right, so by inspection, do any photons leave one and impinge on one? No. With confidence, I can say, hey, if it's not concave, it's convex. It's just the opposite. So this is 0. Then from the summation rule, we remember the summation applied to surface 1 is all that leave 1 and hit on 1 plus all that leave 1 and go to 2 is equal to 100%. We just concluded that that's from the summation rule. Now we know that the view factor 1 to 2 is 1. Now, Frank, what did you use? Reciprocity. You went to reciprocity and you said that the area 1 times the view factor 1 to 2 is equal to area 2 view factor 2 back to 1. True or false? True. And so this allows me to calculate the view factor 2 to 1, which is the view factor 1 to 2 times the area 1 divided by area 2. The view factor 2 to 1 we said is 1, so it's area 1 divided by area 2. What is the area of a sphere? 4 pi r squared or pi d squared. Is it pi d squared? Pi d squared, yes. And so you could even put here the pi d1 squared over pi d2 squared, or d1 divided by d2 quantity squared for the view factor 2 to 1, d1 over d2 quantity squared. Or leave it in areas, whatever. And then how do I get, we just used summation, how do I get f2 to 2? It's the summation now, right? So we just have the summation that says view factor 2 to 1 plus the view factor 2 to 2 is equal to 100%. And so the final f2 to 2 is 1 minus view factor 2 to 1, which is d1 over d2 quantity squared. True? Good. They only get harder. They only get more challenging. But you'd be better at, okay, I can use the summation now. Oh, I can use reciprocity now. And I can calculate the view factors. Here's another example. You have an inclined, parallel, infinite plates. It's easier to show just a cross section. So the infinite plate looks like that and like that. They are infinite plates of equal width. So this is W, the width of the top plate, and this is W, the bottom plate. And they have a common edge. Right there's the common edge. It's going off into the third dimension into infinity. This is the angle theta. And you talk about the surface 1 and the surface 2. And for this combination, for this problem right here, the view factor 1 to 2 is equal to 1 minus the sine of alpha over 2. 1 minus the sine of alpha over 2. What I want to do is I want to pause. I want you to try and see if you can establish that fact. How would you establish that fact that the view factor 1 to 2 is 1 minus the sine of alpha over 2? All right, so we introduce a third surface to complete an enclosure. And the two sides of that enclosure are length WW. I need to find the length of side 3. So draw split alpha in half. Won't that be a 90-degree triangle now, both on top and bottom? So I can find the length of this line. The length of that line, the hypotenuse of that right triangle is omega W. So is it W sine alpha over 2? So the area 3, let me do it like this. Area 3 is 2 times that, 2W sine alpha over 2. Make sense? What is the area 1? W. What is area 2? W. I'm not multiplying by some depth. It's the length of the line is proportional to the area. Okay. Now that we have worked out that, you make the brilliant observation that the view factor from this imaginary 3 to make an enclosure back to surface 1 is related to the view factor from 3 back to surface 2. What is that relationship between these two view factors? Is that is what?
They're equal.
They're equal. How do you get that they're equal? Because basically it's symmetrical, right? So it's symmetrical. So there's no preference to go to the other side, the 1 side or the 2 side. If they come off a 3, 50% are going to hit 1, 50% are going to hit 2. True? So you make that observation right there. So what is this equal to? 1/2. All right, we're almost there. So now think of going the view factor area 1, view factor 1 to 3, and do area 3, view factor 3 back to 1. Let's do this. Do I know the areas? Do I know the view factor? I can get this view factor 3 back to 1. What is the view factor? 1 back to 3. 1 to 3. What is it equal to? Area 3 divided by area 1, view factor 3 to 1. What's area 3? W sine of alpha over 2. What's area 1? W. View factor 3 to 1 is 1/2.
Is area 3 2 times omega?
Oh yeah, 2W. Thank you. 2W. Messed up on that. Look at that. You guys are fast at getting that fixed. So the view factor 1 to 3 is sine of alpha over 2. We go back to summation rule. We say the view factor 1 to 1 plus the view factor 1 to 2 plus the view factor 1 to 3 is equal to 100%. The view factor 1 to 1 is 0 because it's a flat surface. So now finally we get that the view factor 1 to 2 is equal to 1 minus the view factor 1 to 3. So the view factor 1 to 2 is 1 minus sine of alpha over 2. Done, right? There are a lot of configurations and a lot of these view factors tabulated and put in equations or plots in the chapter. Now, let's use the view factor to make calculations of radiation exchange between black surfaces. So if I have a surface 1 and a surface 2, and surface 1 and surface 2 are at different temperatures, there will be a net exchange of radiation between them. So Q net from 1 to 2, let's just say 1 is hot. Okay, so I'm thinking that's the direction for the flow. 1 hot, 2 cold. The net transfer 1 to 2 is equal to how much is coming off of 1. Somebody says, tell me, what is the number of watts? What is the power, radiative power coming off of a surface 1? Wouldn't it be the size of the area of 1 and then the black body emissive flux or power of 1? I know the book, I like to use flux, but it uses just power, black body emissive power. Wouldn't that give me the units of watts? It's coming off of it, right? Surface 1 is black, so there's no emissivity here. It's 100% what comes off. Then I have to multiply by the fraction that get the 2. That's how many watts are leaving 1 and getting to 2. And because both 1 is black and 2 is black, there's no emissivity on 1, and everything that gets to 2 is absorbed. But that's the one way. The back way is that we have the area 2, and then we have the black body emissive power of 2. That's how many watts are coming off of 2. And if we multiply that by the fraction that go from 2 back to 1 and subtract it, won't we have then that's the net transfer? Remember, a surface is always emitting photons. So even if it's colder, it's just emitting fewer watts of photons. All right. So this is the equation for the net exchange. What is the relationship between F1 to 2 times A1 and F2 to 1 times A2? They're the same. They're the same from reciprocity. So a lot of times what we'll do is we'll put it like this. We'll put it just F1 to 2, we'll put it like this. A1 F1 to 2 times EB1 minus EB2. Remind me, what is EB equal to? Is it sigma t to the 4th? Stefan-Boltzmann law, chapter 1. Integrate Planck's distribution, and there you go, Stefan-Boltzmann. So what drives the radiative transfer is not the difference in temperature, but the difference in the black body emissive powers, which is proportional to temperature to the 4th power. So the flow net of heat transfer from 1 to 2 is equal to this equation. Well, we just think about electric resistor analogy. We say, what drives the flow? A difference in the black body emissive power divided by some resistance. And that resistance is given a name. We'll call that resistance the radiative resistance due purely to the geometry between the two surfaces. That's all it is. So it's a geometrical resistance, how well they see each other, how big they are, as well as how well they see each other. And so somebody might say, well, that resistance, it's 1 over A1 F1 to 2, or 1 over A2 F2 to 1. It's the same thing, the same magnitude. So that's our geometric resistance. I don't think I have time to solve this problem. I'll solve it next time. Thank you very much. We'll see you Friday.